We are Capstone Group 10.1. The members are Peyton, Dara, Stefan, Aaron, and Michael. We were challenged to design and build a cart system that can balance a single, double, and ultimately triple inverted pendulum. The design project is intended to show the testing process of a single pendulum and its changes moving towards the double and triple pendulums.
The pendulum begins the process with the swing up. Once the pendulum has met the conditions to leave the swing up, balancing begins. Finally, the pendulum returns to its set point after adjusting from the external force acting on it.
The following figure 1 is our 3D render showing the single inverted pendulum track and structure build. The design includes a linear drive belt that moves the cart and an encoder to keep track of the pendulum's angle as it attempts to swing up and balance.
We would like to point out a few of our key components. First is the Arduino Mega 2560, which includes 54 digital I/O pins with 15 PWM pins. Our rotary encoder was used for the fast data processing. Our H-bridge currently acts as our motor controller, and our geared DC motor has a gear ratio of 10:1. Some of our mounts needed to be custom developed for our system. For starters, we have a single pendulum encoder mount, which sits on top of our cart and collects data for the single pendulum. Next, the motor mount, which secures the motor to the edge of our structure, allows for a stable belt drive. Finally, we have the double and triple pendulum encoder mounts, which were developed to have the encoder sit on top of the pendulum rods.
The wiring schematic for the single inverted pendulum can be seen in Figure 11. Every component is powered through a 5-volt rail and grounded from a common rail. The motor driver is the only component wired to the external 12-volt power supply. Both the motor encoder and the pendulum encoder have their outputs connected to the internal interrupt pins on the Arduino. Future pendulum encoders would be wired identical to the encoders seen in Figure 11.
Moving on to our software overview. Once the program is started, it initializes all the variables used and sets up the various input and output pins. After that, the program waits for a start signal. Once the start signal is sent, the swing up begins. So long as the pendulum is not at the top, it will continue to swing. Once at the top, the balancing begins. If the pendulum ever falls to a place that it cannot be recovered, the program ends to prevent damage to the hardware.
The first thing that the pendulum does when the program is initiated is it begins a swing up process. This takes the pendulum from its initial downward state and swings it up until it is vertical with relatively little motion so that the balancing part of the program can initiate. So the first question we have to ask when programming something like this is, how do we know that the pendulum is going to balance? To evaluate this, we look at the total energy of the pendulum system and we compare that to the energy that the pendulum would have if it was perfectly vertical with no rotational energy. If the total energy in the pendulum is less than that of a perfectly balanced pendulum, we know we need to add energy to the pendulum in order for it to swing upright and reach the vertical point. If the total energy is greater than the perfectly balanced pendulum, we know the pendulum is going to overshoot and we have a chance of not being able to move fast enough to catch this in our balancing program. We can find the total energy of the pendulum system simply by adding the pendulum's potential energy to its kinetic energy. Using the rotational speed of the pendulum's current angle, and the velocity of the cart that the pendulum travels on, we can determine how much energy needs to be added or subtracted from the system by using the formula on the screen now. The controller uses this formula during the swing-up process to adjust the cart's speed in order to add or subtract the appropriate amount of energy to the pendulum. Once the pendulum has swung up, the balancing portion of the program begins. PID control is used for the computations here because of its ability to reduce oscillations in the system while maintaining its given set point. In this case, 2 unique PID controllers are used. The first is dedicated to keeping the pendulum upright by maintaining an appropriate pendulum angle. The second controller keeps the cart centered on the track by adjusting the angle the first controller is trying to meet. The combination of these 2 controllers keeps the pendulum stable, upright, and the cart centered on the track. Thank you for your time and enjoy the rest of the Tech Expo.